Right, so we've discussed the first two of the five members of the five tuple in the formal definition of M. Now we do the third one, which is the very heart of the proof. So to find the delta for big M, the transition function. Now, here it is. Here, this line here is the core, the very heart of the proof, in my view. Right? So, what's it doing? Well, it's taking a current state of machine M, right, where R1 here, the first member of your ordered pair. The R1 here, that's the current state of machine M1. Okay? And this, the second member of the ordered pair, that's the current state of machine M2. Okay? And in comes the current symbol, the symbol currently being read in the input stream. Okay? Call it alpha. Well, so you now want to create the next state of machine M. Well, what will that be? Well, it'll be an ordered pair, right? And remember, the first member here will be the next state of machine M1. Well, you know what that'll be. You just use the transition function of machine M1. So this here will just be D1 of R1A. Right? Remember, R1's the current state of machine M1. That's the transition function for machine M1. So you can calculate what the next state will be for machine R1, and it'll be that. Okay? So whatever state that is for machine M1, put it in as the first member of the next state of machine M. Right? That's sort of the essential idea. And similarly for the second member, the second part of your ordered pair. So this here should be the next state of machine M2 when it reads the same symbol, the current input symbol A. Okay? And assume the current state of machine M2 is R2. Okay? So using the transition function for machine M2, you can calculate what the next state will be for machine M2, right? By using this. Well, get that value and make it the second member of your ordered pair for machine M, right? So that's how you define your transition function for M in terms of the transmission functions of your two machines, M1 and M2. Right? Rather cunning, don't you think? It's a nice way to handle it. So the person who dreamt that up, I think, had a brain or two. Right? So it's a rather nice proof. Okay. Right. So you take your current state of M1. You look at the input signal coming in, and you calculate the next ordered pair, the next state of machine M, and you do that by calculating the next state for here and here by using the transition functions of machine 1 and machine 2. All right. Now the fourth, so that's the core of it. The rest is sort of pretty much detail, but the main idea, the brilliance. The intellectual content, if you like, of the proof is, well, this line, effectively. Right, starting state for Q0, well, remember the states of machine M, they are ordered pairs of the states of machine M1 and M2. Well, what's the starting state of machine M1? Well, it's Q1. You can't see it's in the previous session. But anyway, the starting state for machine M1 was Q1. So and the starting state for machine M2 was Q2. So, okay, so that pair, the starting state machine M1, the starting state machine M2, that ordered pair, that will be the starting state for machine M0, which we've labelled Q0. All right. Now 5, the set of accept states for the machine. Well, remember the basic design idea was, besides the ordered pairs, like this, was if one of the machines accepts, then if M1 or M2 accepts, then M will accept, right? So you need to define an F. By definition, that's the set of accept states for machine M. Okay. So now it'll be, the states of machine M are of this form, an ordered pair, where that's the current state of machine M1, that's the current state of machine M2. So your set of accept states will be these ordered pairs where either this or both is in an accept state. So if R1 is in an accept state, assuming the input string has been read, right? It's gone through, it's been finished, the reading has been finished. And you look at the final state of machine M. Now, if so you're trying to find out the states that would be accept states for machine M. And those accept states for machine M, in other words F, will look like this, where either, now the tape has been, the input string has been read, okay? So either this is an accept state for machine 1, or this is an accept state for machine M2. Okay? So that's the condition on these members of the ordered pair. So in other words, R1 belongs to F1, right? That's the set of accept states for machine M1, or R2 belongs to F2, and that's the set of accept states for machine M2. Okay. All right. Now you can do this as homework if you like. If you think about it, you could rewrite this as just this. Now that may not seem obvious at first. I had to think about it a little bit, but now either this is in F1, right? It's an accept state for machine M1, or this one is in F2. It's an accept state for machine M2. So another way of writing this is this way. So in other words, R1 is in this, is one of these accept states, and then you don't care about what this is, right? It could be anything, any Q2, or it's R2 is an accept state of machine M2, and then you don't care what state the first machine 1 is in. Hope that clarifies that. All right. Now note that this F is not just the Cartesian product of F1 and F2. Okay, because if it were, then you wouldn't be talking about the union. Your operation wouldn't be the union. You'd be talking about the intersection of these two languages. Have a think about that. In fact, if you did this, you would be giving a proof about that this class of regular languages is closed under intersection. Okay? But we're not talking about intersection, we're talking about union. So this is not, this F here is not this. It's not the Cartesian product. It's it's this or this. Right? Okay, so well, that completes the construction, right? With in a sense, that's the end of the proof, and the rest is really just commentary, because if you're going to create a proof by construction, and you finish the construction, what's the end of the proof? Right? Now, how do you know the construction then is